I think we'll get started even though people are still coming in. Welcome to this seminar, which is part of the joint working group meetings that have been happening this week. We're pleased to have Dillon Amaya here from NOAA. Dillon got his PhD from Scripps and then did a postdoc at CU, and he's been a long-time visitor and collaborator with CAS. He's now a federal research scientist at NOAA down the hill, and today he's going to tell us about using the Mesa Clip simulations to do predictions with analogs. So thanks, and the floor is yours.
Yeah, thank you. I got it. Test, test. Is that good? Good? Okay, awesome. Hi, everybody. Thanks, Isla, for the introduction. Thanks for, are we asking for the door? Yeah. Okay, yeah, I'll get the door. Okay. Yeah, no worries. We'll get there. Thanks for having me. Always excited to get out of the building, especially in these trying times, to interact with folks. I'm going to try something new today. This might be the first time ever that I have fewer slides than I have minutes to talk. So we're going to see if I can get us out of here a little bit early, or if I'll wax eloquent and keep us for the full hour. But today I'd like to talk about creating skillful high-resolution seasonal climate forecasts using a statistical technique called model analogs. And I added a plus here because this was an abstract I submitted to the winter meeting. And I was given a little extra time to talk, so I threw in a couple extra exciting results that I think you might find interesting as well. So there's a little bit more than that in here, but that is the crux of my presentation. Want to acknowledge my co-authors here, Mike J. Cox at the NOAA Southwest Fisheries Science Center, Mike Alexander also with me at NOAA PSL, Ho-Xuan Wei, who is a CIRES research scientist, Joe Barsuli, longtime CIRES research scientist, Matt Newman, formerly of CIRES, now at NOAA PSL, and then Steve sitting in the back. So I appreciate everybody's contributions to this work. So just getting started here, I wanted to give you a sense for the kinds of problems that NOAA works on, and specifically where I fit in within NOAA. I'm part of what's called the NOAA Marine Resources Team, which is part of the Atmosphere, Ocean Predictions and Predictability Division. And I work on, at the highest level, I work on climate variability and change and its impact on US coastal waters. I particularly focus on the California current system, and the reason for that is that there's a large range of sensitive marine resources that need managing. So we interact a lot with folks in the Southwest Fisheries Science Center, helping them understand what are the environmental drivers of things like threatened and endangered species, marine and coastal habitats, commercial fishing. There are other marine resources that may not be living and breathing, things like recreation, offshore wind, which may no longer be a thing, and subsistence harvest. Another one that's not listed here that our team is certainly focused on are threats related to coastal inundation. So thinking about coastal flooding and infrastructure that needs managing and dealing with. So that's largely what we do. And I would say that the concept of marine resource management is a relatively new one in the spectrum of managing things in the federal government. And because of that, there is this growing desire for ocean forecasts to support those marine resource management decisions. And this is just a figure taken from Tomasi et al. 2017 that sort of illustrates the intersection of a variety of different marine resource management decisions that can be made on a variety of different space and timescales, and the different climate and weather phenomena that intersects those decisions. And I would say that it's become increasingly apparent in maybe the last 10 years or so that we can leverage the evolution of and what makes these different physical processes deterministic to help manage marine resources and all these decision-making that need to happen on these different time and spatial scales. And that may be obvious to folks that think about NWP or have been thinking about weather forecasting for the last 50 years. I would say that ocean forecasting is where weather forecasting was maybe 3 decades ago, right? There's this really exciting time where folks that are in fisheries are uptaking environmental information in new ways and actually beginning to trust it to make decisions. Historically, that has not been the case. There are the fisheries managers historically have not leveraged environmental input because they know those waters the best. They don't need to tell you. They don't need you to tell them what the temperature is going to be in 6 months because they know where the fish are going to be based on their stock assessments. So it's been not necessarily a battle, but has definitely been an ongoing discussion to build those relationships in the marine resource community so that we can ultimately help them make better decisions. But because that conversation is certainly ongoing, it's certainly developing, there's been a lot of issues in terms of ocean forecasting from the modeling community as a whole. For one thing, ocean forecasting is often hampered by low model resolution and very limited oceanographic output. And this is just an example of the modeling resolution issue. The figure on the left here, stage right, audience left, is just your typical NMME 1 degree couple climate model simulation, CAN-CM4. This is one of the models that is outputting seasonal forecasts every month that we get our precipitation and temperature seasonal outlooks from NOAA CPC. And then on the right is a regional ocean modeling system simulation, a regional ocean model that's run at 10-kilometer resolution. And you can already see like the big difference between a 1 degree model and a 10-kilometer model in terms of the representation of the coastline. In the 1 degree model, you have land grid cells in the ocean grid cells on the land. Whereas in ROMs, you're starting to resolve a lot of those more regional effects of islands. Certainly, you're resolving the shelf a lot better, particularly in places like the California current system. The continental shelf is 20 kilometers wide, 30 kilometers wide at most. So you're definitely not capturing any of those dynamics in a coarse resolution model. And you're certainly not capturing the environmental factors that a lot of these sensitive marine resources are existing in. And just to give you a sense of those scales, once again, this is just showing you several of these national marine sanctuaries that exist in California and the spatial scale at which they're making decisions. So we kind of refer to this spatial scale as the community scale. This is kind of where decisions are being made. Certainly there are macro decisions that are made, but a lot of the decision makers that are managing these marine sanctuaries want information at that community scale. So there's certainly a desire in that regard for higher resolution information, whether, and we'll talk about this later, but whether that information is accurate or not based on our representation of the physics. So in terms of oceanographic output and data availability, I just ripped this from ECMWF's user guide for their seasonal climate model, CIRES-5. Basically, it says that some raw data from the forecast is archived to tape, but there are no immediate plans to make ocean data available from seasonal forecasts to users. And this is a problem we run into all the time in the ocean forecasting community, is that modeling centers, operational forecasting modeling centers are not saving oceanographic output to the degree that we would want them. And I think historically it's because they don't see that user base, right? There's not a well-defined set of group of people that want 3D ocean temperature, that want salinity, right? Often you just get SST and SSH. Those are typically the only two things that most forecasting centers will actually save. But we're working to ameliorate some of these problems. There are higher resolution ocean forecasts based on regional models that exist, they're under the development, but they're very computationally expensive, as you can imagine, to run and certainly to maintain for operational forecasting efforts. And I'll just give you an example here. This is a paper from Mike Jaycox et al. 2023, where they used ROMs, and they dynamically downscaled forecasts from CAN-CM4, that coarse resolution coupled model, dynamically downscaled the atmospheric output and forced ROMs to create regional forecasts of the California current system on seasonal timescales. This was very expensive, expensive enough that they could only produce 3 ensemble members and only 2 initialization times, January and July. So obviously you can start to see that push and pull of what's possible computationally with what you're able actually to produce in terms of initializations and lead times that could be of use. One way we're trying to, again, continue to overcome this is through something called the Climate Ecosystem Fisheries Initiative, which was something put together through the Inflation Reduction Act during the Biden administration, which is this giant cooperative, I don't want to say agreement, but cooperative plan between NOAA and fisheries, or between NOAA, PSL, GFDL, and fisheries to develop this integrated framework of creating regional ocean modeling forecasts that are operational, and I mean that in the strictest NOAA standards, operational, to provide real-time information for fisheries uptake, basically. So these are currently being developed at NOAA GFDL primarily and some at PSL, where I sit down the hill. But again, they're expensive, and it's going to take continued support to maintain these systems going forward. So the overarching question here is, can we overcome computational bottlenecks to make high resolution forecasting more viable. And I put ocean in parentheses here. My focus is primarily on the ocean today, but the techniques and tools that I'm going to talk about, I think, are easily applicable to other domains if you're interested in forecasting land surface or the atmosphere, or in my case, the ocean. So there are probably a lot of ways to answer this question. The one way that I think could be particularly useful, and one I'm going to focus on today, is this concept of the model analog framework. So just quick show of hands, raise your hand if you've ever heard of model analog forecasting. Okay, so most of the room, which is great. If you have not, I'll just step through it real quick, but it's a pretty simple idea. It's this idea that if two states in the climate system are very close to each other, they can be called each other's analog. And this is actually kind of an old idea. This is an old Ed Lorenz idea from the 60s, where his thought was if you wanted to predict the weather tomorrow, you could look at all observations of weather in the past, find instances in the past that look like today, and then follow the evolution of the past as a forecast for tomorrow. And it turns out that that does not work at all for weather, but it works really well for climate. And that's because there's a lot of deterministic signals that go beyond the initialization on seasonal timescales, on these climate timescales. And I'll show you some evidence for that. But the way that we can do this on these climate timescales is not by comparing today's observations with past observations. We can compare today's observations with a climate model simulation. So let's say that we had observed sea surface temperature anomalies from January of 1998, and that's what that map is showing. We can compare this observed state to, say, a long pre-industrial control simulation. Let's say it's CSM1's 1,000-year long pre-industrial control simulation, and we would compare this map of January and observations to every January in that model simulation. We would find an analog, so something that looks very similar to observations, and then we would follow the subsequent evolution of that analog in the model simulation and treat that as a forecast. And so this is an actual analog. I believe it's taken from CSM1's pre-industrial control. Can't entirely remember, I made it a long time ago. But it is the year 336 here. And you can see that it has a lot of the same characteristics of observations. So there's a lot of benefits to model analog forecasting. One is that it's, I hope you can tell, it's very inexpensive. It virtually eliminates costs associated with real-time forecasting. And so obviously, and I want to talk about this phrase inexpensive for a second, because obviously there's the computational demand of creating a library, right? You have to create the simulation that you draw analogs out of. So there is a computational demand to that. But when you think about operational forecasting, the cost isn't so much the production of the model that you're going to use in operations. It's the sustained cost, the people cost, the computational hours to keep that going in real time in perpetuity. And this is something that NMME is constantly struggling with. There's constant push and pull of, is NMME viable? Can we keep it going for another year, another 5 years, right? Where are those resources coming from? And this is one technique that can help overcome that because it is so cheap to maintain in real time. You just have to run the model once, and then you're done. Additionally, you can forecast any variable that the model simulates. So even though I'm making matches based on sea surface temperature anomalies, you just do that to find the right climate state, what part of the attractor you're sitting on. And then once you've identified that state, you can follow the evolution of any variable from that point and make a forecast. So this, for ocean forecasting, this overcomes a lot of issues in terms of saving model output, right? I can now forecast anything in the ocean that is produced by the model. In that vein, you're saving a lot of extra variables, but now there's also fewer issues related to long-term storage of forecasts. And at high resolution, that's a big problem. How do you save all these high-resolution forecasts in perpetuity? Well, the nice thing about analog forecasting is that because it's cheap and because it's fast, you often don't even have to save the output for very long. You can always just rerun the forecast, right? As long as you don't delete your library, you can always recreate the forecast very quickly. This is perhaps one of the most important parts of analog forecasting. There's no initialization shock or drift. You already start in the model's biased state. You don't drag the model to reality, and then over the length of the forecast, it would drift back. You just start where the model already is on its own preferred attractor, and it's already biased, and so there's no drift over the length of the forecast. So you actually can improve early lead forecast skill as a result. And then finally, any model with a sufficiently large library can make a forecast. This technique turns any model into a forecasting model. So that can be any pre-industrial control from the CMIP archive. That can be the CSM2 large ensemble, or any large ensemble for that matter, which makes it a really powerful tool to also evaluate a model's biases, because I would say the most rigorous test of a model's skill is how well it can predict the real world. And this is one way to test that. So moving on to results here, I'm going to separate my results into two sections here. I'm going to provide you some evidence that model analog forecasts work in the way that I'm describing, and then I'll show you, hopefully having convinced you of that, I'll show you some high-resolution model analog forecasts in the California current system. Okay, so luckily some of this evidence has already been done for me. This is a paper from Hui Ding et al. In 2018, where they created analog forecasts of sea surface temperature anomalies in the tropical Pacific. This is SST forecast skill at 6 months lead for two CSM models, CCSM4 and CSM1. Analog forecasts are on your left, and the corresponding NME forecast, which is a fully data-assimilated initialized forecast, is on the right. And what you can immediately see is that the analog forecasts in the tropical Pacific, well, in the global tropic Indo-Pacific, are as skillful, if not more skillful, than what's coming from NME. And this is also true of a variety of different models from different modeling centers, whether that's GFDL, NCAR, or in this case, the multi-model mean as well. You get the added benefit of signal to noise when you look at the multi-model mean effect, but overall, they found that analogs were competitive with NME. So I'm going to take that a step further. I'm going to compare analog forecasts of something noisier than SST, like preset, and I'm going to try my best to reproduce SMILE, CSM2 SMILE. And just as a refresher, CSM2 SMILE is described here. I'm going to be looking at forecasts within SMILE from 1979 to 2019. The forcing scenario for SMILE is listed there, and these are the general initialization fields for SMILE: FOSSI, JRA55 in the atmosphere, and TRIND for land. Obviously, there's 4 initialization times and 20 ensemble members. I'm going to try to reproduce SMILE by drawing analog forecasts from the same model that is under the hood of SMILE, right? The CSM2 large ensemble, where I'm going to take my library now will be the 50 members that share the same radiative forcing scheme as SMILE. So I have a library that's 2,500 years long. Every calendar month has a library of 2,500 years. And I'm going to draw analogs based on comparisons to monthly mean FOSSI. So now I'm using the exact same initialization field as SMILE is using, but now I'm just creating analog forecasts based on matches to that initialization field. And I'll do that from 60 south to 60 north. Obviously, there are no limitations on ensemble size or initialization times, but I'm going to try to make it as apples to apples as possible. And then I'll take a step further, and I'll instead draw analogs from the whole CMIP6 pre-industrial control archive. So there are 33 models we'll draw from. And I'm also going to compare to FOSSI SSTs to create those analogs and show some comparisons to NMME. So this is all, yeah, please.
How do you choose the 20 members for the...
Yeah, so the matching criteria is comparing the SST anomalies from 60 south to 60 north to FOSSI. So I'm treating FOSSI as observations in this case, and it's based on reducing the mean squared error in that domain between observations in the model. Yeah, good question. Okay, so how well does this work, right? This is showing August initialized seasonal precipitation skill in SMILE. So for the first 4 seasons of the forecast, obviously you can go further. And you can see that SMILE does some really good things going out to a year, out to JJA here. So how does that compare to what's coming from the analogs? Well, you'll see that far from the initial condition, CSM2 model analogs that are drawn from the CSM2 large ensemble are largely indistinguishable from what's coming from SMILE. And one piece of evidence for that is if you take the difference, which is that last column there, you can compare the hindcasts between SMILE and the analogs using a Fisher-Z transformation statistical test to say whether that one hindcast is significantly better than the other. And so stippling here is telling you where that's true, is where one hindcast is better than the other. And so if you see blue values, that means the analogs are statistically significantly better than SMILE. And where there's red and there's a stipple, it says SMILE is significantly better than the analogs. And you can see that there aren't tons of coherent patterns here, right? This probably wouldn't even pass field significance. So largely, these two systems are basically the same, and that makes sense, right? The underlying model for SMILE is CSM2, right? And so once you lose the memory of the initial condition, the evolution of the model attractor should be basically the same, and that's what we're seeing in the forecast space. So I'll expand on the initial condition here a little bit as well, and we can look at, instead of seasonal forecast skill, monthly forecast skill. So this is just showing the monthly forecast skill of precipitation, again, for an August initialized forecast in SMILE and the analogs. The analogs are initialized at this 0 month, which is the month before you actually want to start the forecast, so it'd be matching on, for August, it'd be matching on July SST maps. But you can see that SMILE, which is initialized in August 1st, it has that memory of the initial condition. In that first month, SMILE is undoubtedly better, right? It has that memory of the initial condition. But as that forecast goes on and you get far enough away, you can see these patterns start to converge, and you're basically just following the model's evolution, which is the same between the analogs and SMILE. So one more piece of evidence for that is this is a time series that's showing global precipitation pattern correlations for 3 different combinations of model and observation. So just focus on the black for a second. It's just saying for every year, I'm taking the pattern correlation of SMILE precip forecasts at 1 month lead with what's happening in observations. And so SMILE has 4 initializations. I do that for every initialization, and I average them together to get the black line. The gray line, same idea, but taking the pattern correlation of the analogs and observations. And then the red is showing the pattern correlation between SMILE and the analogs. So the black and gray are a measure of skill, and the red is a measure of how well the analogs are able to reproduce SMILE. How good of an emulator are the analogs relative to SMILE. And you can see at 1 month lead, there's a big gap between the black and the gray, and that says SMILE is better than the analogs, and that makes sense because that's where the initial condition is. And there are modest correlations in that red line over time. But again, as we get further away from the initial condition, so let's say at 3 months lead, you can see the black and the gray lines converge, and the skill of the analogs and SMILE over time are basically the same. And you can see that red line goes up, right? Analogs are becoming an increasingly good, quote unquote, emulator of SMILE. And I put that in quotes because I know emulator means something else to different people. I'm just saying in this case, SMILE, or the trajectory of the forecasts and the analogs are very similar to what's going on in SMILE. And that emulation is strongest in periods where we would expect to have a lot of skill, right? INSO years. You see the red line go up during big El Nino or La Nina years, and that's when we get a lot of the skill to begin with. There are periods certainly where you get less agreement between SMILE and the analogs, but we don't have a lot of skill there anyway. There's nothing deterministic about the system, so it's just randomness from SMILE versus randomness from the analogs, and those 2 random bits aren't overlapping. So that's where you don't get the strong emulation. Okay, so one more comparison, and I'll move on to high-res stuff, but this is now going to be comparing, I'm going to move on from SMILE and now expand this to the whole CMIP6 archive, and how well can we produce analog forecasts drawn from the 33 models in CMIP6 that have pre-industrial control simulations. This is showing August initialized precipitation forecasts verifying in the following winter, so something like a 5 to 7 month long forecast. And this is coming from the ensemble mean of 7 models from NMME. And these are the 7 models that are currently operational, currently used to create our seasonal precipitation outlooks that you can go online and see from CPC. And so this is the same map now from the CMIP6 model analog forecasts. And you can see that there's strong comparison between what we're getting from NMME and what we're able to reproduce using the model analogs drawn from the CMIP6 in wintertime. And just to zoom in on some points of interest, these boxes are highlighting different regions where we would expect to see some kind of deterministic skill, primarily related to INSO teleconnections. The box offshore is where we actually get INSO skill. The southwest box over land is where we want INSO skill to be, and it's not really there a lot of the times. And then the box in the southeast is where we do get INSO-related skill over land. And so we can see how the skill of the analogs versus NME line up in those 3 regions. So the top row is offshore, the middle row is the American Southwest, and the bottom row is the American Southeast. These are skill grids, and I'm going to show a lot of these. So I'm going to step through how to read them just a little bit here. The x-axis is a different monthly initialization. The y-axis is the forecast lead time. And in this case, these are seasonal averages. So there's only 10 months here. It's just, so for example, a January initialized forecast at 1 month lead would be a JFM forecast, or 2 months lead would be a FMJ or FMA forecast, and so on. So what you can see here is that NMME does outperform the analogs in some of these boxes, particularly that offshore box, and to some extent that southwest box, but in the southeast, they're almost identical, which is really cool to see. So I'll just highlight again here that analogs, I'm not going to claim at any point today that analogs should replace data assimilative models, because there are some advantages to those, to that setup, but I think they can certainly augment what we're already producing in real time. Okay, so all of that precipitation analysis was to hopefully convince you that analogs do something sensible. So now let's return to our initial question. Can we overcome computational bottlenecks to make high-resolution forecasting more viable using the model analog method? And now all we need is a high-resolution library to produce high-resolution forecasts. And thanks to you guys here at NCAR and elsewhere, Texas A&M and the like, we have access to MESAClip, right? The CSM high-resolution simulation, CSM 1.3, which has this 10-kilometer ocean and a 25-kilometer atmosphere and land. And there's a large data library there, 500-year pre-industrial control simulation, and now a 10-member historical and future simulation, which can be mined for analog forecasts. And so that's what we're going to do here to produce these forecasts. So the way I'm going to do that here is I'm primarily going to be focusing on forecasts of the California current system. And I'm going to compare current observations to the CSM high-res data library, which is going to be the last 350 years of the pre-industrial control simulation. And that's because, as I understand it, the first 150 years is not usable. There was some sort of hardware issue. So there's 350 years in the library. I'm going to compare observed SSTs in the global tropics, which is the green box, and the California current system, which is this orange box. And the specific selection method that I'm using here is I'm minimizing the distance between the OBS and CSM high-res using mean squared error in the tropics, so the domain average mean squared error in that green box, and the domain average mean squared error in the California current system, where the mean squared error in this case is area-weighted mean squared error as normally calculated, but importantly, these parameters are normalized by the domain average variance. And that's so that you're capturing the model's variability relative to observations, and you're basically bias correcting the model's variability, which gives you overall better matches. And this is a standard technique that has been used in model analog forecasting. One other thing I'll mention here is that I'm equally weighting the tropics and the California current system. And that's an important choice. If you do not equally weight them, if you just say, I'm going to match on the tropics and the CCS, weighted by latitude, you overemphasize the role of the tropics and you don't get a good initial condition in the California current system, which is important because in the ocean, that initial condition is skill for 6 months, right? Because the ocean is so sluggish, you get persistence forecast skill. So you need a good initial condition, you need some good representation of the tropics, and not equally weighting them, equally weighting them helps accomplish that. And I have some figures later in the extra slides if folks want to look at that. Last thing I'll mention here is that I actually make the matches at 1 degree resolution, and there's some reasons for that, which we can talk about if you're interested, but it's important to know. So once I find the matches, once I find a match, let's say I'm matching December of 1997, I find the top N analogs, I then follow the evolution of the model at that higher resolution. So even though I'm making a match at 1 degree, I follow the evolution of the model at its native resolution of 10 kilometers in the California current system, and that's my forecast. So then you can average the top N members or the top N matches to create an ensemble forecast. And in this case, the time equals 0 or lag 0 would be December of 1997. Lag 1 month would be January of 1998, and then so on. And you can do this for as far out as you have model simulation, basically. So the way I'll do this is the way I'm going to produce the forecast is by matching to detrended SST observations from OISST. And the hindcast period that I'm going to evaluate the skill for is January of 1994 to December of 2019. And it's a relatively short period because that's where we have the best high-resolution observations with which to verify against. Specifically, I'm going to verify the forecast against this GLORIES ocean reanalysis, which is a 1/12 degree ocean reanalysis that's extremely realistic in the California current system. We've done a lot of work to validate GLORIES relative to unassimilated observations to make sure it's doing something sensible. I'm going to keep the top 20 matches, and I can show you how that choice is sensitive to, or how that choice affects skill. But before I move on, I really want to highlight here, you'll notice that a lot of these individual matches, have very strong mesoscale variability, as you'd expect with a 10-kilometer resolution model. But when you average them together, you cancel out a lot of that random mesoscale noise, and you're left with a high-resolution version of a large scale signal, right? This is kind of the instance signal that you'd expect. And so I want to emphasize that I'm not making mesoscale forecasts. I'm not trying to forecast fronts or eddies or filaments. This is a physically consistent high-resolution forecast that is leveraging large-scale signals like INSO. And there are some other benefits to doing that. So it's not enough to just use a coarse resolution model to get to this. There's some benefits to having that high resolution that we can talk about. Okay, so how well does this work? Just to give you a baseline of how much scale we might expect at these resolutions, I'm going to show you some initial comparisons to this dynamically downscaled regional model that Jaycox et al. Put together. So they had those 3 ensemble members. This is SST forecast scale at 3-month lead for January initialized forecasts. And now stippling here is insignificant skill. So no stippling is good. You get good skill. So overall, the ROM simulation does a nice job. It gets some skill in the Pacific Northwest. We can now compare that to the top 3 matches from our high resolution model analogs. And then I'm taking the difference on the right. So right away, you can see that the analogs are doing something at least comparable to what's coming from ROMs. In some places, it's improving the skill. In some places, it's degrading the skill. But because the analogs are so computationally efficient, I'm not stuck at 3 members. I can increase my ensemble size to 20, for example. So once you increase the number of ensemble members going into the forecast, you get better signal to noise. You're capturing the dynamics coming from, in this case, the tropics better. And you're getting enhanced skill throughout the California current system. And now you can really starting to see that benefit of a larger ensemble size. Now, obviously, to be fair to the regional model, if I could increase the number of ensemble members in the regional model to 20 members, you'd likely get a similar map to what's going on at the bottom. So it's not one model is better than the other. This forecast system is necessarily better than another forecast system. This is mostly demonstrating the benefit of signal to noise, or having a higher signal to noise by having a larger ensemble, and that the analogs are at least doing something similar to a more computationally expensive counterpart. So in terms of why am I picking 20 members, right? This is just giving you an example of how sensitive that choice is. This is showing SST skill averaged within 75 kilometers of the US coastline. So it's just really in a coastal band up and down the US West Coast. And it's showing you the skill for every combination of ensemble size that the library can produce. So it's either 1 member out to 349 members. And you can see that forecast skill peaks pretty quickly. It actually peaks around about 50 members, but you get most of the way there at 20. So we're sticking with 20 just for efficiency's sake, but this just gives you a sense for how sensitive skill is to the size of the ensemble. Importantly, you don't want to get too deep into your library, because at some point you're pulling out crap matches, right? You're not really getting good matches. And so it's going to degrade your skill. And this is just to highlight that this isn't sensitive to initialization time. This is the same map, but for a July initialized forecast from all of them. And again, you can see that the analogs are doing something at least comparable to the regional model, and also improving upon the regional model when you can increase that ensemble size. Okay, so again, one limitation in current operational ocean forecasting is that we aren't saving things that we care about. We just often get SST and SSH, but there are a bevy of variables that fisheries are interested in, and this is going to be an example of all of those variables here. I'm going to take forecasts averaged within 75 kilometers of the US West Coast, so that's within that black contour here. And now we can look at the forecast skill as a function of initialization on the x-axis and lead time on the y-axis. And this is what we're getting for sea surface temperature, and I'll describe the stipples in a second. But we're going to expand that to 9 other variables, so 10 other variables. They include sea surface height, bottom temperature down to 1,000 meters. So this is bottom temperature on the continental shelf. Buoyancy frequency, so stratification of the upper 200 meters of the ocean. Mixed layer depth, surface currents, surface wind stress, and wind stress curl. And the reason why I selected these 10 variables is because they're among the most common physical variables used to force species distribution models. So often fisheries folks will take these physical variables, force a species distribution model, and tell you where cod is going to be, or Dungeness crab, or something similar that we're interested in eating, right? So we want to be able to demonstrate that we can forecast those physical variables well in a nearshore environment. So here the stipples are now saying significant skill is in black, and then significant skill when persistence skill is not significant is in white. So that's kind of a measure of when you're getting additional skill from dynamics, things like isotelic connections, and it's not just about that having a good initial condition. So white and black stipples are both good things in this case. So what do we notice, right? We notice that for surface variables and for things with strong persistence, we're getting good skill like sea surface temperature and sea surface height. Bottom temperature has strong persistence related to it. There are some good dynamical reasons why we might also get a lot of white dots on bottom temperature, what we can talk about. Things that we can't predict well, we may not expect to predict well, are things like wind stress, right? It's a noisy field on seasonal timescales. We don't necessarily expect a ton of predictability there. What does this look like in space? So this is showing the 3-month lead forecast skill at that 10-kilometer resolution for all of these variables. But this is for all initializations. So there's obviously some seasonal cycle to that. We just saw that in the grids. But I wanted to give you a sense of where we might expect skill in space. And there are some variables like SST that are just skillful forever and wherever you're at. But sea surface height is one of those variables that's very skillful in that near coastal zone. And that's, spoiler, is related to coastally trapped waves in the model. That's not something that you would resolve in a coarse resolution model, right? That's physics that we're not necessarily resolving, and it's giving us extra skill in that nearshore environment. Obviously, things like bottom temperature, we're not going to be able to capture in a coarse resolution model. That's that right column is just showing bottom temperature, and you can see how narrow the continental shelf is, right? This is a place where we get really sensitive demersal species, so things like Pacific cod or Dungeness crab that live on or near the seafloor, and they're not particularly mobile, right? So they care very much about the temperature of the water, and if you have a marine heat wave on the seafloor, right, that's something that you're going to want to be able to predict. So having bottom temperature is another important factor. This is just meant to highlight, these skill grids can change depending on where you average, basically. Before I was averaging all up and down the US West Coast, but you can break that down into regional averages, and there are some, like I said, some variables are skillful regardless of where you're at. But something like buoyancy frequency, we didn't see a ton of skill averaging the whole coastline, but you can see that there is quite a bit of skill in buoyancy frequency in the Southern California bight, basically. So what's driving a lot of the skill in the analogs? Well, obviously, one feature that you can hopefully pull out here is this diagonal band. And if you're used to looking at these skill grids in places that are strongly influenced by INSO, you'll see these diagonal bands. This is the INSO signal. It's saying that regardless of where you initialize the forecast, you're going to have skill in that following winter. And that's because there's deterministic signals coming from phase-locked INSO in wintertime. And I don't have to tell you how INSO gets to the tropics, but I'll show you some pretty pictures. Obviously, there's, P&A pattern is going to drive wind variability, which forces the surface ocean and can lead to predictability. But then there are these coastally trapped waves again. This is a coastally trapped wave that was observed during the 1997-1998 El Nino event. This is taken from the Glory's ocean reanalysis. You can see it slithering up the coastline from, as an equatorially trapped Kelvin wave, converting into this coastally trapped wave that goes all the way up to the Gulf of Alaska over the course of about 120 days it takes to get from the far west Pacific up to the Gulf of Alaska. And the spatial extent of that wave is set by the Rossby deformation radius. So it's relatively large in the tropics, about 100 kilometers, but the further you get up into the mid-latitudes, it's getting down to 40, 30, 20 kilometers. So you really need that higher resolution modeling, high resolution physics to capture the spatial extent of these signals. So one more fun thing that analogs can do is it can help you understand where predictability is coming from in a more holistic way. So for example, I initially made my matches based on the California current system and the tropics, but what if I had just chosen analogs based on the California current system? What if I didn't match climate states based on what's happening with INSO, and I just went after a really good initial condition? Well, so I can sort of demonstrate, just focus on the middle, these two here, demonstrate what you'd get for skill in that case. These are each of those variables again, and this is just a January initialized forecast versus a July over all these lead times. And you can directly compare this forecast skill to what you would expect to get from persistence. And what you'll notice is that a lot of this skill is front-loaded, it's early in the lead times, and it looks, mostly captures that skill related to persistence. We're able to get a really good initial condition, and then we just let it dampen, right? It just dampens, and you get skill associated with that. But if you say match on the tropics, and only the tropics, and you say initialization be damned, and you're just getting that deterministic signal, you can see now a lot of that skill in the summertime is now backloaded. It's giving you a lot of skill when you're forecasting the winter. So that would be at lead months, 6, 7, 8 would be DJF, right, for a July initialized forecast. Whereas for a January initialized forecast, you're not getting any skill at long leads because that's summertime, right? You get all that skill associated with INSO teleconnections in the winter, and then by the time you get to summertime, all that deterministic forecast skill is gone. And then just to sort of bring it, so this mostly captures skill related to tropical teleconnections. And then just sort of to bring it all home, if you include both, which is what I had been doing, right, you get that combination of the two, combined skill of persistence and tropical teleconnections in that way. Okay, so hopefully this is providing you some confidence that you can create skillful forecasts of high-resolution ocean, the high-resolution ocean environment in the California current system. How do we hope these get used? There are a lot of these ecological indicators that are used within fisheries that are based on environmental indices that help them make decisions about where to put their nets, basically. One of them is a habitat compression index. I'm not going to go into the precise methodology about how you calculate a habitat compression index, but basically it's just measuring the amount of cold water that's pressed up against the coastline associated with upwelling. And if that cold water is really close to the coastline, whales are going to follow the nutrient-rich water where all their food is, and they're going to be really close to the coast, and it's going to lead to a higher likelihood of ship strikes and net entanglements. So being able to predict the habitat compression index is something that is actionable when it comes to fisheries management. Another one is this temperature observations to avoid loggerheads total tool, which is essentially just SST anomalies averaged in the Southern California Bight. When waters get too warm in the Southern California Bight, loggerheads like that warm water, they come in and then they end up getting caught through bycatch. So you're trying to catch something else and instead you catch turtles, and that's not great. So you can use this total tool to recommend closures in drift gillnet fishery during the fishery season for drift gill nets, which is the summertime. So you can recommend closures in June, July, or August based on the SST anomalies in the preceding 6 months for each of those recommended months. So just to give you a sense of how well these forecasts are capturing that, you can see that there's a lot of skill, right, in both the habitat compression index as well as the total tool. So it is something that is actionable and useful, immediately. Okay, so that's all ocean. I'm going to return back now I want to bring this back home to other folks in the room who may not care so much about ocean forecasting. Maybe you're interested in atmospheric forecasting, seasonal precipitation forecast, for example. This high-resolution framework still works for high-resolution precip forecasts. And by high resolution now, I don't mean convective permitting. I just mean that 25 kilometers that's coming from Mesa Clip. This is that same August initialized forecast, and now forecasting the following winter, now at that 25 kilometers. And this is based on the top 10 members verified against ERA 5 from 1991 to 2020. So you can see, again, a lot of skill in places where we'd expect it. And we can directly compare that, again, to what's coming from NMME. So these are the 7 models that are currently operational in NMME to produce our seasonal outlooks of precipitation. And I would argue that the analog map is hard to distinguish from any of these NMME models. So again, it's competitive in that way. Okay, so quick summary, and then I have one more thought. High-res model analog ocean forecasts drawn from CSM high-res are cheap and are at least as skillful as expensive alternatives based on regional models. Obviously, it was extremely expensive to run Mesa Clip, but you only had to run that model once, and we're able to get sustainable high-resolution forecasts in real time. I stole my thunder there. Could provide a computationally efficient method for providing high-resolution ocean forecasts in real time. And I do think that this method is applicable to other domains like the atmosphere or land. Okay, so one final thought, and then I'm happy to take questions here, is I kind of skipped the most obvious question at the beginning here. Is like, do we even need high-res forecasts, right? This quote haunts my nightmares. You were so preoccupied with whether or not you could, you didn't stop to think if you should, right? Is it worth the time and effort that it takes to create a data set like Mesa Clip from a forecasting perspective? Especially if coarse resolution models can largely capture the variability at regional scales in places that are driven by large-scale dynamics like INSO teleconnections. And that is true for some things. I'll give you an example here. So this is just showing from Glory's ocean reanalysis, the spatial decorrelation length scale, a sea surface temperature for different locations along the US West Coast. So each dot is just the nearest grid cell to the coastline in Glory's for different locations. And then the corresponding contour that matches the same color as the dot is encompassing grid cells within Glory's that are correlated with that dot at least 0.9. And the shading here is just distance away from the coastline. So if you think about a 1-degree model, each of those intervals from the shading is 50 kilometers. So 2 intervals would kind of represent a 1-degree cell away from the coastline. You can see that at 80% variance explained, you might not be able to capture a lot of that with a coarse resolution model. But let's say you had a lower tolerance. What if 80% wasn't, what if you're okay with 60% or so, right? You can see now that, yeah, coarse resolution models could capture a lot of that regional variability for SST. And if all you really cared about was an e-folding scale, go crazy, right? Coarse resolution models can largely capture what's going on in the very near shore environment because of this large scale forcing of the surface through things like atmospheric teleconnections. But this isn't necessarily true for every variable out there. This is the same map for sea surface height. Sea surface height is pushed around by the winds, but it's also driven by coastally trapped waves in the California current system. You can see that a lot of the spatial decorrelation length scale is on that wave guide, basically, which is kind of cool to see. Same idea for mixed layer depth. Mixed layer depth is a very noisy field. You can see that the spatial length scale, decorrelation length scale, is not extending very far off the coastline, and you wouldn't necessarily expect a coarse resolution model to represent the regional scale variability at these different locations. Okay, so returning to this question is, do we even need high-res forecasts? Well, there's a lot of benefits that I see immediately from this. One is that coarse models may capture regional variability of some variables, but not all. And I was just trying to demonstrate that with this previous figures. But also, it promotes uptake by users. You know, the end users that I'm working with in the fisheries industry, you know, whether it's fair or not, they see a high-resolution forecast and they think it's better for them. Even if it's not necessarily more accurate from a physical perspective, they think it's more accurate for them because it's more at their community scale. And so there's a real value from an uptake perspective of having a higher resolution system. Presumably, going down to higher resolution gets better physics, which should lead to better skill. Again, I say that presumably, right? If we get better representation of mesoscale air-sea interactions, you know, maybe we're representing the impact of SSTs on precip better, so we get a better forecast of precip over land, something like that. I think there's a lot of work to be done in that space to see if that's actually how it plays out. But then, you know, access to additional variables relevant for decision making, like bottom temperature, is not nothing, right? Those are environmental factors that are relatively poorly observed, but you know, can be simulated in a high resolution space that people who make decisions are going to want to see, and you can't get that from things like coarse resolution models. Okay, so I'll return to my summary here. I'm happy to take any questions. If we don't have a chance to chat, there's my email, and we got some time, so I appreciate it. Thanks, everybody.
Okay, thanks for a great talk. Any questions for Dillon? Yep. Are they good on the ceiling mics? Yeah.
Okay. Thank you, Dillon. A very nice talk. We looked at the coastally trapped waves in the California current, and the low resolution model can capture the phase, and it is slightly surprising when it's 100 kilometers. I think what we found, the high resolution model had a higher amplitude.
Yes.
So there's some kind of advantages to high resolution, but it was surprising that the low resolution got something which it was a surprise to me.
Yeah, that's a good point. And I'm happy you brought that up. We did look at something similar in ECMWF CIES-5 model, which is, it's actually run at a 1/4 degree, but they output it at 1 degree. And that model does have coastally trapped waves that are dampened relative to reality. Yeah. So it's a good point.
Keith?
Nice presentation, thank you. When you have your 20 analogs from your forward running model, your initial states have the 20 analogs. Have you considered weighting the forecast based upon how close they are to the state that you're trying to mimic? Does that make sense? I don't know if I phrased it well.
Yeah, so yes, that is a way of combining matches into an ensemble, is by weighting them by how close they are, by their RMSE, basically.
Yeah.
Yeah, that is a method that can be used, and it ekes out, you know, maybe another 5% of variance explained. So in the scenario, I haven't tried it for this particular method. When it was applied to tropical SSTs, in that Ding et al. Paper, they saw about a 5 to 10% improvement. So it is something. I will emphasize that there's a whole cottage industry to optimize the analog selection method to get the best forecast possible. And that's a machine learning problem that folks like Libby Barnes and Kenya Turide and CIRES is working on. But yeah, that's a good point. There are these other methods to combine your matches into something useful.
Kirsten?
This is kind of related actually, but you equally weighted the tropics and along the California coast. I was wondering, for the 10 variable example, did you look for analogs for each of those variables and then weight them together, or were you only using SSTs? I'm sorry if I missed that.
No, I didn't. I was not clear, so thanks for asking. everything's based on SSTs. So even the atmospheric variables that I'm trying to predict is just based on matches to SST.
And do you think that would improve your skill at all if you were to look for analogs for the other variables as well?
Yeah, absolutely. Yeah, you can certainly optimize the selection criteria to forecast the thing you care about. So if you care about precip in the American West, you can optimize your selection criteria to match on precip in the American West and get the best forecast you can, for sure.
Dave?
I think it's just related to that question then. So, you know, I was curious why like the mixed layer depth or other variables other than sea surface temperature and sea surface height were not really being well predicted. That you would have thought mixed layer depth is kind of having exerting some influence on the SSTs. So there's.
This is go back the way I want. So mixed layer depth, we actually do have some skill in the wintertime. It was one of those with the diagonal. So there's some INSO skill for mixed layer depth in the top right. And there were similar with the surface currents. I mean, the things that we were not predicting well were things like wind stress and wind stress curl. I think partly it's the way I displayed the skill averaging up and down the coast. I think there's some regional characteristics that come out more easily in the maps, where you can see that we are getting wind stress skill more in like the Northern California region. And that's might be where, in this model, at least the INSO teleconnection is most, consistent relative to reality. So you're getting that impact on coastal winds, which affects upwelling, leading to impacts on the subsurface, like stratification, but also SST. I think that's where that's coming from.
Steve?
Great talk, Dylan. I'm wondering if you detrended before you verified against observations, and if obviously you have to do that to find the analogs from a PI control, but are you leaving skill on the table on seasonal timescales by not including the external signal?
Yes, I am leaving skill on the table. I did detrend the observations. I was curious how well we could predict the variability. For what it's worth, the trends in the California current system aren't big relative to other places. If you did the same exercise for the US East Coast, all of the skill is trend. There's very little deterministic forcing on the variability there. So there are ways to add the trend back in when it comes to analogs. You could draw analogs from PI control and then add a trend from the CMIP archive of historical simulations, or the historical simulations from Mesa Clip, for example. Ding et al. 2019 explored that. So there are ways to add back in that trend skill.
Any other questions? Rich?
You showed ACC, but have you ever done an analysis, the kind of hit false alarm kind of analysis to see whether you're, whether it says more about exactly how you're evaluating?
Yes, I have a couple examples of that for precipitation. I don't have that for, I did do it for the ocean side, but I'll just show you some of those examples for the precip case. This is Breyer skill score, where the top are the analogs, Breyer skill score for the lower and upper tercile, and then this is the NMME Breyer skill score for the lower tercile for all the 7 models coming from NMME. So you can see that there are some deficiencies with the analogs when it comes to these probabilistic skill metrics. And I think that has more to do with the ensemble size that I'm using. Turns out that you get a better analog forecast, probabilistic forecast with a smaller ensemble. The bad matches really mess up your distribution for probabilistic forecasts. So there's some playing around to really see how you can best maximize that hit versus false alarm. And then that's the lower tercile, this is the upper tercile for precipitation.
So if you're not getting the local wind stress, along coast wind stress right, doesn't that mean that you're not getting the strength of the local upwelling correct? So I'm surprised that you're doing so well in SSTs if you're not getting the local upwelling strength correctly.
Well, we are getting wind stress curl to some extent. So I just published a paper in GRL where we look at wind stress curl forecasts from NMME. And so a lot of these models can reproduce or can capture. There is predictability in something like wind stress curl, which maps onto upwelling. I think in the nearshore environment, SST is definitely influenced by upwelling, but there's obviously the big there's heat fluxes that are driven by the winds that help you get that SST signal too, which may not be predictable. The wind itself may not be predictable on those longer timescales, but the reddened impact of the wind on the surface ocean is predictable, right? Because you flare up the SSTs and then they decorrelate over some timescale, right? The Hasselman model at that point. Does that make sense? I feel like I'm not answering that very well.
So in the California, are the big signals really from the tropics? when you get ENSOs and not?
On seasonal timescales, the biggest signal is ENSO.
Yeah.
Yeah, far and away it's ENSO, for sure. And ENSO obviously maps onto upwelling strength. But because wind is so noisy, it's often hard to capture. Yeah. Yes.
I also found on monthly timescales it's dominated by the teleconnections from the tropics. But I think if you were going down to less than a month, when you have the synoptic events locally, then that's when the local upwelling is important.
Yes, yeah. I have yet to make this work for subseasonal timescales. That's another active area of research, is analog forecasts of subseason, like weeks 1 to 4. It's really hard to do better than persistence because there's very little that's deterministic about that timescale. And again, there's an optimization problem here. You could try to optimize your analogs to select on MJO state and try to capture MJO teleconnections on those subseasonal timescales. It's very much an open area of research. But seasonal timescales, this really works well.
Related to that, have you looked at your skill split by ENSO, so El Nino, La Nina, and neutral?
I have not, others have. It's pretty symmetric, yeah. But the California current system is, I would say, asymmetrically dominated by El Ninos. But if you look at like model analog skill holistically over the globe, it's pretty symmetric.
Any questions? I had one quick last question.
Sure.
When you showed the skill as a function of the number of the analogs, I'm not sure I understood the diagram correctly, but on the far right, are you using all of your analogs?
Yeah, it's including every possible match in the library.
Oh, so not every single, I was confused about why there's skill, but so they all have some match? Or is this every year from
From the
the
PI
simulation?
control, yeah.
So you're basically initializing with climatology from the,
Yeah, so I think this is the reason why you have any kind of skill at those bigger ensemble sizes is because this metric is ACC. And so you're basically taking something at the beginning. I'm not gonna touch it, I promise, but I'll just point. Up here, right, there's matches that look like what you're trying to match on, and there's deterministic information up here, and you're averaging over that. But down here, it's just random matches. At some point, you're anti-correlated with your match, but all of these random matches eventually cancel out. So it's just like the large ensemble. You're canceling out all of the noise at these worst matches, and what you're left with is the deterministic part. And so that gives you some skill even at bigger ensemble sizes, but it's driven by the best matches. Does that make sense? If I showed this for Breyer skill score, it's way more peaked. You basically get no Breyer skill score for these bigger ensemble sizes. So yeah. It's a good observation though.
well, thanks for the great talk.
That'll be
Cafeteria if anyone wants to do that.